outside salesperson and contractor support. So who supports me is a team of technical people because I'm not very smart. So anything that breaks or anything highly technical, we deploy a team to come out on site, fix your problem for you, do any kind of training or anything like that that you need. A lot of times, as you'll see with this kind of stuff, we can do it remote, which is one of the big positive things about DDC and a building automation system with DDC in it. So we can basically, square you away with whatever it is that you need. My contact info is rob@stromquist.com. That's probably the best way to get a hold of me. What we're going to cover today is 3 parts. We're going to give you about 5-10 minute break in between each one. So the first hour is going to be intro to DDC. So we're going to talk about from the ground up, basically what DDC is, what it means, what brings it all together for you. I want everyone to ask as many questions as you want. If you guys don't ask questions, we'll be done in about 25 minutes. So a lot of it becomes just kind of discussion from you guys. Don't be shy, don't be bashful, just raise your hand or give me a hard stare and I can kind of pick up that you want to ask something. There are no stupid questions. The whole point of this whole thing is that when I first started to try and learn this stuff, I had these smart guys that I was telling you about trying to teach me these things, and you kind of get to the point where it becomes pretty basic for you, and you have a hard time getting it basic enough for somebody else. I mean, think about something that you guys know really, really well, and then you get somebody that comes to work with you that doesn't know anything about what you're talking about. Sometimes it's hard to get that basic. Well, this class is designed to get as basic as we possibly can. So for some of you, the first 15 or 20 minutes is probably going to be a review. That's good. Soak it up. After that, we'll kind of ramp it up pretty quick. And then when we get into hour 2, we're going to talk about what Tridium is, what Niagara is, open systems versus closed systems, and why those are good and bad. And then the third hour, I'm going to turn it over to Michael, who's going to give us a really in-depth technical piece on communication protocols. By show of hands, who in here is more like on the technical side, like, working on systems, that type of stuff? Basically, you're not sales. Raise your hand. So if you are sales, raise your hand. Okay, good. So we got a little bit of a mixture of both. So it seems like the majority of you guys are more non-sales related, so we'll try and touch on that a little bit. What I always like to do is get just a few people to kind of share what it is that you came here to learn. Something that I've always wondered this, and what is that? You guys got anything? Who's going to be the first person? It always takes about 20 seconds for the first person to raise their hand, and then after that, everybody else kind of goes. What did you come here to learn? What's something that you thought? You wore the yellow jacket and you sat in the front row, man. I mean, what else was I going to
do? Where I work at, we use the building automation systems to control different components in stores, retail stores. So I come here to get more information about building automation systems.
Okay. So when I say BACnet and LAN and Modbus, are those terms that you guys are familiar with? Or just something that some of you have never heard before? Okay, some head shaking. No, it's good. You're in the right place. If you've never heard of that stuff, you're in the right place. Somebody else, what's something that you've always kind of wondered what it was, and you thought it kind of pertained to DDC? One more person and we'll get started. Don't everybody raise your hand at once.
Run the question again. What?
What's something that you came here to learn? What are you curious about? Do you want to know how to spell DDC? I can help you out with that real quick.
No, just to see how some of the systems are internet interfacing together a little better.
Okay, perfect.
BACnet.
Gotcha. So what we're going to basically do is give an overview, go over basic terminology, communication protocols, networks, hardware, all the benefits of a DDC system. Then we're going to go into the system architecture. System architecture is essentially how it's wired and configured within the building, right? So you're going to come from the head controller to all the controllers that are going on the various equipment within the building. We're going to build that from the ground up. So by the end of this, you'll be able to understand how An entire building automation system is networked throughout a building. And then finally, we could talk about open systems. You're going to hear all the time people talking about open systems, and we have an open system, and we have an open system, and blah, 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 blah. And the reality is that the majority of the time that someone says they have an open system, they actually don't have an open system. So you guys are going to be the experts, and you're going to be able to tell by the end of the day when these guys are not knowing what they're talking about. All right? So what is DDC? Anybody know? It's too early. Nobody is going to give any feedback. You got it, man. Direct digital control. So the Webster definition, there's not really one, but the internet definition is the automated control of a condition or process by a digital device. So basically, when we're breaking this down, automated, so obviously we know what automated means. It means that we're going to make some parameters, we're going to set it up, and then from that point there, it's going to do its own thing automatically. We're not going to have to touch it. When we set it up, as long as it's working the way we want to, the seasons aren't changing, nothing's drastic, we're not trying to get more efficient. We essentially are going to program this system, and it's automatically going to do what it needs to do, okay? When we say digital device, what we're talking about is a controller that's basically like a computer with basically no moving parts within inside. If you take the plastic cover off of a controller and you look inside, you're just going to see a microchip or a motherboard or something like that. There's nothing in there like a pneumatic system that's moving around. Now, of course, the actuator and stuff's going to move. That's a little different. But the controller itself and the brains of the system, it's a digital device. It's smart. It's a smart controller. You hear smartphone all the time. It's got its own brain, does its own thing. What I like to add to this is that it will also communicate, because you could have DDC set up how I just talked about when you would call the application standalone, which means that you're just putting a controller on a machine. It's a smart controller. You're programming it to do what it needs to do, and it just does its thing all day. Well, that's great, and that's a huge improvement over a lot of the pneumatic systems and a lot of the other systems that you see in the past or currently today. But if it's not communicating with other pieces of equipment in the building, then really you're not really doing what people are going to call DDC today. Okay? Does that make sense? Any questions? At that point, you'll be doing automation. All right, BAS. What's that?
Building automation system.
You got it. A building automation system, so a computerized intelligent network of electronic devices designed to monitor and control HVAC, mechanical electronics, lighting systems in a building. So if you think about it, could you have a building automation system but not DDC? You could, because technically the pneumatic stuff that you see out there is a building automation system, right? Because at some point you're setting up all your pneumatic controllers to do what we talked about, automate, right? And they're going to carry out their process, and you're not going to have to go and change this and change that. I mean, imagine if we had to be the actuator or all these different pieces of equipment and get ladders and whatever else. So a pneumatic system is a building automation system. But now we've kind of gotten past the point where pneumatics aren't really thought of that way. Technically they are, but DDC is really what makes up today's building automation system. Okay? All right, so let's talk about benefits. So lowers utility cost. That's the big thing. That's why all of this came about. That's why pneumatic controls came about. That's why DDC came about, is because at the end of the day, people want a return on their investment. What's the point of going out and buying all this new fangled-dangled stuff? What's the point of taking this pneumatic stuff out and putting this new stuff in if it's not going to lower my utility costs, right? I want to save money. I want to get a return on my investment. Reduces maintenance costs. If I go in and I program a lead lag scenario where I have two pumps and I want to alternate the runtime on each pump, give this pump a break for a little while and then let this one go and then swap that out, obviously I'm going to reduce the maintenance cost because I don't have both of them coming on all the time, or I don't have none of them, working, that kind of thing. Maintains measured comfort. Obviously, the whole goal of HVAC is to what? Keep us comfortable, keep us where we don't have germs floating around the building, getting us sick, that type of stuff. Reduces occupant complaints. Think about this one. A lot of you guys in this room have got to come a-running, as I say, when somebody in your building is complaining about being too hot or too cold, right? And I'm sure that all you guys are just like the Maytag man that's sitting at your desk with your ESPN the magazine with your legs crossed, just sitting there waiting for somebody to call you, right? No, you're never not doing something that you'd rather be doing when somebody comes for you to come a-running. So if we can get a good system in place for you, that we can cut down on this stuff, and we can cut down on the times that people are calling you guys to come say, hey, I'm hot, or I'm cold, or this isn't working, or that's not working. That's a big deal for you guys, right? You guys can be more productive. That brings us down to increased productivity. A lot of studies these days are showing that while we may save you 5% to 55% on your energy bill, we may be able to prove that we can save your company even more money by making you guys more productive, making the tenants more productive. People say that if you're too cold, like, women are the worst offenders, I'm sorry, but if they're cold, they're going to go warm up. They're going to go get a jacket. They're going to go walk around. They're going to do something. If they're comfortable, they stay at their desk or wherever it is that they work, and they're more productive. Guys, same thing. If you're hot, you're going to go stand under a fan for a little bit. I do it all the time. Holy crap, I got to get off that roof and come in here and cool myself down, right? So increased productivity. They found that in schools, there's a lot of grant money to come in and retrofit these systems. So they found in schools that if the building is more comfortable, it cuts down on sick days. It keeps students more productive. So when you cut down on sick days, there's money that comes to the school that says if your attendance is this or better, we're going to give you extra money. So if we can get you extra money, we can tie that in for you sales guys that say, if we can get this going for you, there's this extra money that'll pay for your system, right? If the students are more productive and they can learn better, well, then they're going to get higher test scores, and we all know that there's a big thing for that. To get higher test scores, you get more money. Seems like these days everything's centered around money, but that's a whole different presentation. All right. So how's it done? Well, the first thing is controls. We've already talked about that. Smart controls. Stick them on our unit. We program them to do what we want. They automate themselves. It's a much, much, much smarter control and a much easier program. The building runs a lot more efficiently. Outside air optimization, this is really neat. There's a lot of things changing with this as well too. So outside air optimization is, if we weren't bringing outside air into this building, larger buildings are way more impacted than smaller buildings. Like your house, you're not bringing outside air into your house. You don't need to. Opening your door and that kind of stuff enough to make that work for you. But in these large buildings, you've got to bring in a certain percentage of outside air, because if you did not, all you would do is recirculate this air that was inside. You'd have an extremely efficient system, because you just be pumping out 72-degree air and recirculating it over and over and over, and your system would hardly ever have to work. But every time that somebody coughed or sneezed, any kind of dust or crap like that ends up on the floor would just stay in the building, and over time you develop what they call sick building syndrome. I'm sure there's a much more technical term for it than that. But you would develop that over time, and everybody in your building would start getting sick, and then we decrease that productivity, and then we're back to square one. There's actually ASHRAE standards that stipulate how much outside air you have to bring in per the square footage of the building and how many occupants you have at any given time. Now, as a part of DDC, they're actually making like ion generators that they'll put into the building, and ASHRAE says that if you produce these ions that go in and kill bacteria on their own and go out into the space and infect this stuff, that will actually allow you to bring less outside air into the building, and because you've got that mechanism, and then it's killing bacteria and stuff. So that's pretty neat too, and that can be part of your DDC strategy, your building automation strategy for your customers, is install an ion generator everybody know what ions is? I probably should have clarified that. So ions are naturally occurring in the air. If you go to more rural areas and like, well, there's not a lot of people and cars and stuff like that. Like I think of Switzerland or something like that, high up in the mountains. You know, everybody's smelled that fresh country air, right? Well, that's ions. And so we can actually determine we can make ions. And Albert Einstein is actually who determined that we could make them way back when. So those come in and they automatically start killing bacteria and stuff like that. And you can buy these things for your house too. It's really neat. The impacts in your house, you'll everything in your house will smell a lot better. Really neat stuff.
You're actually talking about ozone in general.
Well, yes, but the new stuff doesn't create ozone.
Really?
So a lot of the older stuff that you're talking about, you don't hear it very often because it emits ozone, and ozone's bad for you.
That thunderstorm smell, that's what ozone is, essentially. And I think it was so stupid for the EPA and FDA to get all riled up about it.
Yeah, but it's a little different than if you're, outside and you can kind of smell it and that kind of thing, and then, if it's ozone in your building. So our stuff, and then like I said, it's a whole different presentation to sell you our ion generators, but it's ozone's bad. Cold plasma generation is the new stuff, and that's what's good. So you're going to start seeing a heck of a lot more of it because cold plasma generation is relatively new. And you haven't seen a lot of the old stuff because it does, like this gentleman said, produces ozone, which is bad for you. So on one hand, you've got really good ions going in and killing bacteria, but then you're putting this ozone stuff in your building and there's kind of, canceling each other out. Good. Scheduling. That's pretty easy to think about. So if you left your lights on in your house 24/7, obviously you're going to have a higher power bill. If you ran your HVAC thermostat down to 65 degrees and wore a coat in your house and it wasn't wintertime, it was summertime here in Georgia, obviously you're going to waste a lot of energy. So if we can go in and we can write a schedule for your building that says we're open from 8 a.m. to 5 p.m. and we want the set point to be this, and we want you to run the equipment for your space temp to meet set point. And then after 5 o'clock, we're going to set back and we're going to go to a higher temperature. You're going to save money. You would be astonished. You see it a lot more prevalent in light commercial instances where a building about our size or smaller, well, they just have thermostats on the wall. They have programmable thermostats they never ever programmed. Those guys are, for the most part, running 70, 72, 73 degrees, 24/7, 365. Now, they have their own type of building automation system, which is the office lady that yells at everybody and says, before you leave, you go turn that thermostat down to whatever it needs to be, or turn it up to whatever, and when you get here in the morning, you do it. So that's their own type of building automation system, but that doesn't, what? Automate, right? Because she's not going to remember to do it every day, and we're human, we're certainly not going to. So scheduling is great. Graphical operation, we talked about the time that you guys are deployed when you have to go out and fix whatever is wrong. Well, what if I had a graphical system, which I know a lot of you guys have seen, that tells you there's a problem before you can even know that there is a problem. So all of a sudden you go away from set point. May not be enough. If I went over there and turned this off, it'd probably be 15, 20 minutes, a half hour before somebody said, it's a little hot in here. But that graphical system, we can set it up that it's going to say, hey, boom, something's off. This went bad right now, or something's not working. There's, the controller up here is bad, whatever. So you can actually go and get ahead of the game and go fix something or go start working on something before your tenant ever even knows that there is an issue, right? Graphics are the greatest thing about a DDC building automation system. We talked about coordinating equipment and smarter control. All right, so let's jump into the lifeblood of what brings a DDC system together. Our controllers. So controllers have all manufacturers a lot of times are going to make all different types of controllers for all different types of equipment. And it's a constant race to determine which controller is better and which is different, and what's your price per I/O count and all this kind of good stuff. But the controllers are the lifeblood of your system. Give you a few examples of what this is. So this is a Honeywell Spider. Anybody want to take a wild guess as to what kind of equipment that controller would go on? You got it. Go ahead. You're on it.
PIU,
VAV, PIU. You got it. So what we have is an onboard actuator right on that controller. So you wire it up with your terminals here and here, and then that goes right over the damper shaft that's sticking out of the PIU or the VAV box, and everything's controlled right there. Okay, it's a little bit different than what you've seen in the past, where you've got an actuator, wired up to something else in the space, whether it's a pneumatic actuator going back to some pneumatic piece of equipment or controller or something like that. This is kind of my new favorite controller. EasyIO is a company you've probably never heard of, but you guys have, in your buildings, probably all had something from EasyIO in it, because they make a piece of software that we're going to go into in a little bit, that a lot of manufacturers end up using, or contractors I should say, end up getting from EasyIO. But what makes this so neat is it's a 32-point I/O controller, which is a lot of I/O, and it's capable of doing its own graphics, its own scheduling, its own alarming, its own trending. So essentially, it's a full-blown system all in one little controller. So pretty neat. Just one off to the right, I throw that up there because that's an XL15 from Honeywell, and a lot of you guys have probably had that in your system. That's been replaced by the unitary version of this Spider here, for the most part, but there's still a lot of tried and true folks that understand this and know how to program it, and just prefer doing it that way. There's always something that we know that could be done easier, but we just know how to do it the harder way, and that's just the way we stick with. That's where that XL15 is. Still does its thing, it's just really hard to program. Off to the left is the unique controller from Johnson Controls. It's a PCG. It's a unitary controller, so it's used on air handler units and rooftop units and that kind of stuff. But it's a little unique in the way that it programs. So remind me, I'm going to pick on the guy in the yellow shirt again. When we get to configurable and programmable controllers, remind me to talk about that one, all right? He's going to pay attention really. He's been paying attention the whole time anyway. All right, so I talked about I/O a little bit. So I/O is inputs and outputs, and I know that you guys probably know that. But when you break down I/O, you got to look at it in different things when you're wiring up a controller, because a controller doesn't all come with universal I/O. You got to know what it is. So if you have an analog input or output, it's got to go to a piece of hardware or something like that that accepts analog. So when it's analog, think of number, all right? So it's temperature, humidity, velocity, pressure. So if you have a set point that you want to program, or you want to display a space temp in there, coming back to your graphics or coming back to your controller or going out to your actuator, you're going to need an analog input because it's a number, right? 72 degrees, it's a number, right? Digital is basically it's contacts used for starting and stopping. So think off and on, occupied, unoccupied, open, closed, okay? And then universal, it's everybody's dream. I don't know why they don't all just make them all universal. It probably has something to do with money or something like that. Is that your I/O? Any questions on that? Comments? All right, so this is that Honeywell Spider again that controls a VAV box, and I just want to point out a couple different things. We talked about how you've got the actuator already on board here, color-coded inputs and outputs, so you can easily tell which are digital, which are analog, and which are universal. You got your pressure sensor up here. Remember what that looks like for a slide we're going to have here in a little bit. It's programmable, different than configurable. We'll talk about that in a minute. These are pretty interesting little things right here. BACnet, address dip switches, and silk bus. So BACnet we're going to talk about in a little bit, and you'll notice that anytime that you're doing anything with BACnet, you can always tell if it's a BACnet controller because it's going to have little dip switches on the controller. So that's how you can perceive to be smarter than other folks, is look at it and go, oh, that's BACnet. And they're looking all over the place and doesn't say BACnet anywhere on there. Well, how the heck did you know that? Well, that Rob guy at Stromquist in that intro to DDC class I took 5 years ago told me if it had dip switches on it, it was BACnet. So Silk Bus is a proprietary COM bus that we're going to talk about in a little bit. All right, this is a typical VAV box. This is not drawn to scale. This is what you may or may not see up above your ceiling in a VAV box. And if, for those of you who don't know it, the VAV box is the, we don't have any here, but you see them in large commercial buildings where you have the air handler units that's, its whole job is to push 55-degree air down the ductwork. And then the VAV boxes are over each zone, and they have a damper up here that opens and closes depending on what the space temp needs to be in that building or that zone, right? And then they actually even have a spot for reheat, so when it actually calls for heat, you'll see different types of reheat, but like this will be electric reheat. And essentially you got a little heat strip in there that heats up, and that 55-degree air turns into whatever it needs to be based on, you know, if they need to be heated up in that space, okay? There's a whole, I think it's 2-day class on VAV boxes. So that's your intro level in 35 seconds. But great class that we teach here if you guys ever need to know more about VAV boxes. So our VAV box we talked about is going to have a controller that's going to mount. This is that onboard actuator here. It's going to mount on the outside of the box, and it's going to pick up this damper shaft that's coming out of the side of it. And then we're going to do all of our wiring to all of our I/O and all that kind of stuff right up there on the box. And then we're going to have a sensor, which is like this over here in the wall. So let's wire this up. Now, in my brain, what I had you guys doing was kind of helping me out, but I can see by the enthusiasm that you guys have shown me this morning, I'm not going to have a whole lot of volunteers. So I'm going to give you the first one. The flow ring, we talked about that pressure sensor. You got little pressure tubes that come off of that flow ring and go into those two little red things I showed you on the spider. All right, so then that damper, you guys think that's going to be an input or an output? So think about it for a second. Output, you got it. Now why is it an output? Good job, whoever said that. It is going to be an output because what we have is, well, I'm giving away the next one, but the sensor is giving the controller the signal of what's going on in the space, and then the controller sends that output to the damper to tell me to open or close, modulate, however I need to be. All right, so the next one's the fan. So what's that going to be? Got a little bit of both. That's good. It's going to be an output. Same thing. Sensor comes in, tells the fan, bring in some more air. Whether it's hot or cold, we don't care at that point. The controller's telling the fan to go do something. All right? So the next thing is reheat. I'm sorry. Next thing. Uh-oh. Well, we really messed it up, Rob. So the sensor we've talked about is an input, but we're actually going to have two things. We're going to have the space temp that it's going to. What is what? So the sensor's got to tell the controller two things. It's got to tell it the space temp in the space, and one other thing. Close. It's got to know something else, and I'm probably going to program this sensor.
Space temp and then set point.
You got it. Space temp and set point, right? because that's what it's trying to get. So that it says, I want my set point to be 70 degrees. And so then it's also measuring space temp. So when I get to 71 or 2 degrees, then it's going to start its program that it's what's programmed to do, and bring it back to where it starts doing its thing, opening the damper, turning on the fan, whatever we've programmed it to do when it gets above or below set point. All right, good. What we got next? Reheat. So think about that again. They can answer too. See, it's all right. I thought he phoned a friend. All right, so reheat is same thing, output, right? So the sensor's telling us what's in the building. We're outputting to the reheat mechanism to say we need to heat this air up, right? All right, lastly, we have a discharge air sensor up here. Does anybody know what a discharge air sensor does?
Yeah, let you know what's coming out of your the vents.
Right. So if you get that graphical alert that says, you know, set point is 72 degrees and space temp is 78 degrees, well, you know that you have a problem, and then you can start before you ever even go up to the ceiling or up to the room. You can pull up your graphics and sit there and look and see, well, what could be the problem? Well, if you see that your fan's on and your damper's wide open, maybe your reheat strip's on because you're wanting heat, but then still something's not quite right. Well, you look at your discharge air sensor and it says 0. Well, you know something's not working. Fan's not working, or the air handler down line's not working. So you can diagnose a lot of stuff right from your desk. These days, right from your iPad or tablet or smartphone. You can stand right underneath it and start pulling up things and trying different things before you ever grab the ladder, which goes back to productivity savings, right? So that discharge air sensor is an input. You got it.
That first thing was a flow, what?
Flow ring. So that's just the, when your air's coming from the air handler unit, it's picking up all the different stuff that it needs to know to make sure you're not blowing up the duct work, to make sure that everything's just the way that it needs to be. There's a lot more technical stuff to it than that, but that's essentially what it does. All right, so a neat little exercise. All right, we talked about configurable versus programmable. This is your time. That PCG, all right. So there's two different ways that you program these controllers, all right? And as you guys, if you ever get to where you're the guy that's doing all the programming, or if you're that guy now, you're going to want to know, is it programmable or configurable, all right? The difference is, if it's programmable, I look at it as cooking myself a hamburger. I have to know every single thing that goes into making a hamburger, right? I have to know that I've got to cook it somehow, so I need a grill. I've got to know that I need to make a hamburger patty, so I got to know that I need hamburger meat and spice and seasoning and all that kind of stuff. And rolled all together, I got to know how to do all that, what else I need. I got to know, most people eat a hamburger with a bun on each side of it and condiments and lettuce and all that kind of stuff. But basically, I have to say, make me a hamburger, and you got to know how to go out and do it. So that's programmable, freely programmable. You just go in, you pull that system up, and you look at it, and it's a blank white screen staring back at you, saying, "What do you want me to do, dude?" And that's what you got to do, is go in there and make your hamburger. All right. Configurable is walking into McDonald's and looking up at the board and saying, "I don't know what half this stuff is, but I'll take that triple cheeseburger baconator on sourdough and those 2,000 calories that come with it. I'll take that, and by the way, just give me a little ketchup and mustard on it as well." All right? I struggle with this analogy sometimes to how to properly make it, but essentially, you're going to basically, if you're a configurable controller, it's application specific. So you're going to buy a controller that's for a VAV box, and it's going to configure, and it's going to come up and say, "I need to know this." I need to know the CFM that the box is. They need to know the, I thought you were giving me the sign. I thought you were telling me to steal second. So it's going to ask you a question, okay? It's going to say next, well, I need to know set point, right? It's going to ask you these things. And you're just going to answer them to the best of your ability. At the end of the day, you're going to program something. Now, whether it works or not determines on how well you answer those questions. But configurable is really starting to become a way that a lot of these guys are starting to go out and just start to program. It's becoming a lot easier. The controls are coming a lot smarter, and it's getting a heck of a lot easier to get out there in these buildings and start deploying a lot of these systems. Configurable, there's some things that are so high-tech and drawn out that you can't do them with an application-specific configurable controller. You've got to be freely programmable. A lot of these really smart guys that have been programming for 5, 10, 15 years, they're going to want to be freely programmable, because it's just sort of kind of like taking the greatest artist that you can ever think of and then giving them a coloring book and saying just color in between the lines. Like, they just don't want to do that, right? They want to draw their own picture and do their own thing. They feel like they can do a lot better picture than what's given to them. Does that make sense? Any questions on this? This is your time. PCG. So PCG is a unique controller because it's configurable and programmable. So when you start it out, it's configurable in that you go through and you answer all the questions, and then you can be done with it, or you can go in and say, well, I want to make a side loop, or I want to do a little bit something extra, little freely programmable, when you can go in and do that part of it. Or you can start right from the very beginning. I don't know why you'd want to on that controller, but you could be freely programmable right from the start. So pretty neat stuff. Johnson Controls sells that. Thank you. I won't pick on any more. You're good. You can relax the rest of the class. I'm going to figure out my next victim here in a little bit. All right.
You know, so it's unfortunate, but wouldn't it be advantageous to have a couple of examples of the modules up here?
Absolutely. We're going to get them for you.
Okay.
They're on their way. They're going to come in a birthday cake, and people are going to jump out with them. So you ruined my surprise. So now I'm just going to bring them in. All right. So the building the system architecture. So we've talked about controllers. So basically what I'm trying to explain here is we've just basically went out and determined that we've got a PCV, because you got the little actuator there, so it's going to go on a, got it. And then these are unitary controllers, so they're going on rooftop units or air handlers or something like that. This is actually a little expansion module that just gives that controller more I/O. But what we've done here is we've gone out and we've installed these controllers onto their respective equipment. All right, that's what we've done so far in this system architecture. That's all we've done. All right. So again, we talked about DDC as direct digital control. And it's the automated control of a condition or process by a digital device that will also communicate. So now we're going to talk about how we make this stuff communicate. Communication protocols. I struggled and struggled and struggled with this, because you'd go out and you'd start talking about all this stuff, and then somebody would say, well, that's great. I've got lawn in my building. Can your controller talk to lawn? Oh yeah, heck yeah, it can, no problem. And I'd come back, and one of the smart guys would go, no, Rob, that's a BACnet controller. It doesn't talk lawn. Oh, crap. And you gotta go back with egg on your face and tell the guy, hey, listen, I sold you the wrong thing. We actually need this, we actually need that. You know, and then the next day I'd go out and the guy would say, well, I've got lawn in my building. And I'd go, well, I can't sell you this. And I'd come back and say, hey man, you learned me well yesterday because I didn't sell it. No, you can sell that because it's BACnet and lawn. Holy crap, you know, stuff gets confusing. And doesn't it get any less confusing, I promise you. You really got to pay attention when it comes down to communication protocols. But they are essentially what allows all of this stuff to do what we've talked about this morning, communicate, all right? The way that I think about it is just a different spoken language, all right? If you think about lawn as Spanish and BACnet as French, And you think about that if the French guy thinks the Spanish lady looks pretty good and he wants to go talk to her, but he doesn't know Spanish, he's not going to get very far unless they both know some kind of sign language or something like that. But for our description here, they can't communicate. All right? They knew other things, but they can't communicate. So the same thing with LAN, Modbus, and BACnet. They can't talk to each other. They just cannot talk to each other. All right? In no way, shape, or form am I trying to tell you that BACnet was invented in France and LAN invented in Spanish. I'm just saying they're different spoken languages, okay? All right. So when we talk about communication bus wiring, you're going to have to wire it up as a daisy chain. This was another one that was kind of hard for me to understand. When you daisy chain something, you're wiring it in a way, let me draw it out for you. So if you look, actually I don't need to draw it. What I had the hardest time understanding is that this red wire here is one wire, and this red wire here is the second wire. And what actually happens is this one goes into this terminal, and both of them get twisted together, the wires, and stuck in the same terminal on that second controller. And then it continues to do that as long as your daisy chain is. Okay? It's simple when it's drawn out there, but somebody just says, oh, you daisy chain it. It's one of those simple things that people just, it's second nature after you know it, and you just assume that everybody else knows what daisy chain is. And when you're standing around with four guys that go, you daisy chain it, and they all shake their head, yeah, what do? You shake your head, yeah, I know what that is. And then you just, maybe you figure it out later, maybe you don't, whatever. So I did a lot of this for a really long time. But the reason that we do that, does anybody want to take a guess? Why would we daisy chain this stuff together?
Parallel,
Okay?
right?
Yep. What else? What happens in a daisy chain if this controller goes bad? Think about the wiring. Remember what I said? We twisted them together, twisted those wires together before we stuck them into that terminal. So if that middle controller goes bad,
You can still read the bolt.
you can still read everything else, right? So we're going to get something on our graphical page that says this controller is bad, but it doesn't kill everything else downstream. You know how your Christmas lights, they're a little different now, but you know your Christmas lights, when one bulb goes bad, the rest of them don't work? Those are kind of like a daisy chain type thing. You got to find that one link that does whatever that circuit burns out, whatever, it's the same thing. So that this wire, if you basically took if you took all the wires out of the controllers and you daisy chain them the right way, you'd essentially have a wire twisted together to another wire twisted together. So essentially you just have one really, really long wire that's made up of a bunch of little wires, right? They're all just going into various terminals across the controllers. Make sense? So that's how you do communication bus wiring.
Whereas if you had that thing in series, obviously, once the wire is broken, it takes everything else downstream, as opposed to parallel.
Well, that
Right.
is wired in series.
Right.
Series is the same as the daisy chain, not parallel.
Yeah, but that's how you lose one unit, and all the rest of them still work because it's in parallel. If you just went from this one to that one, that one, you don't have two wires stuck underneath. That's a Christmas tree light.
Right.
Because one of them goes bad and stops the rest of them down the street and getting their signal.
But you've only got one power supply though, so it's wired in series. The only reason that we're not losing it is because like if you take like an outlet or something like that, you've got power that comes in, power that comes out. If it dies off, you don't have power that runs through it.
Well, that's a
Right?
broken wire.
Yeah, exactly. Well, the only reason that they're not having it there is because they're wiring that and we're going to push them
They're
together.
parallel and off.
I thought parallel was you had individual power circuits running to each individual one. So you have one power supply, but you run that same, one power supply has its own individual wire that's ran to each
Well, that would-
individual component. As far as
That would be
electrical
dedicated.
terminology, yeah.
That would be dedicated supply, power supply.
The other reason we want the daisy chain is it's a much more efficient way for the communications
the 45 or on, or whatever it is, to talk. So that's how you get longer bus runs. That's how you have one bus running through your whole building that's 2,000-3,000 feet. Because if you do like a star configuration and stuff like that, it doesn't talk.
Good questions. All right, so we're building our system architecture. So we got our controllers up there already. I know that's not the best representation of daisy chain, but essentially we've daisy chained these together, and this network is going to be a backnet network. Okay? Does that make sense, everybody? We can add in other stuff, whether it was existing or new. That's one of the cool things about this. From there, we can continue to bring in other things in the building. So if we've got some N2 and some lawn, all in one building, we just daisy chain this stuff together, and all these talk, right? So now all these can talk to each other, right? All you guys that are shaking your head, you're wrong. Because they're not talking to each other, because why? Different languages, you got it. So it would be nice, somebody make a heck of a lot of money if they could come out and determine how to get all these things to talk to each other. When that day comes, it'll be a rich person, right? So as this stuff is, you know, you can't talk to each other, but you can have a whole lot of different boxes talking to each other within a building, all right? But guess what, guys? Too late, somebody's already done it. We're not getting rich. Somebody's already figured out there's this special box that acts as a translator. So this box comes in many different forms and flavors that goes out to your building, and you install it, and then you pull in all your various communication protocols into that one box, and they can talk to each other seamlessly.
So if you have, for instance, we have 5 different programs, and they're not communicating at all. And that's a big problem.
Right.
I'm here trying to just learn to control it because somebody else controls everything.
Right.
We install the VAVs and everything else. We know it's not calling for something, but it's a different program than, say, this building or that building. And the person in control is
Right.
not understanding. So that variable can configure it all together and communicate.
Yes.
Together.
Now, when you say program, do you mean like physical program, like that you log into and you're looking at that does this part of the building, and then a separate program does the other part of the building?
Control the handler to the VAV to whatever, and it could be a different program everywhere.
Right.
And then they're wondering why this is not all working properly. because
Right.
It's not communicating together, and they're spending a lot of money on different stuff it's a government thing.
Right. Right.
Can't communicate.
So the Jason,
And he can't communicate.
Like
He
we-
should be here.
like we have an area called the West Wing area,
Uh-huh.
P1, P2. So in other words, you're tying everything into the Jason. It controls those different areas.
Yeah.
Okay.
And I don't want to confuse you, but you guys have got 11 Jaces out there, I think.
Yeah, we just installed them.
Yeah. Another one in the plant downstairs, that type of stuff. So, yeah, you guys have got a lot of Jaces, and you can have a lot of Jaces because the Jace fills up just like a computer. You know how you pull up your computer and you open up 5 programs at one time and it starts going really slow and crawling? A Jace is a computer. It does the same thing. If you put too many controllers into that Jace, it'll start slowing down. So then you get a bunch of Jaces in a building, and then we'll just call it a master Jace for right now. Talks to all those. All right? So the Jace is the mechanism that provides connectivity to systems within a building. We're going to go into part 2 a little bit more about how this all comes together and works. But essentially, most of the major manufacturers today have a Jace that they deploy out in the system, and then there's, I'm trying not to get too in depth, there's usually 3 models of Jaces. Like small, medium, large, let's just say that for now. And if you were to pop the plastic cover off of either one of those Jaces, what's inside and what you look at that right there is the same across all manufacturers. A little bit of programming difference sometimes. Some people put their embedded cookie cutter program in there, but for the most part, all the Jace is the same, and these folks that make the Jace, they just sell it to all the manufacturers and go out and deploy it. Okay? So back to our system architecture. Now we've got our BACnet, N2, and LAN all pulling into that one Jace. We're not going to get rich because it's already been made. And now it can all talk to each other. So in your situation, one of 2 things are going on in your building. You either have, and this is going to kind of go into more of part 2, but you've got either like this N2 system is its own system with its own form of Jace, because the Jace, remember, is the head unit that allows multiple protocols to talk to each other, but there's also head units that talk to only one protocol. So N2 is a good example because N2 is the Johnson Controls proprietary communication protocol. So you may have in your building part of it's N2 or something like that where it's proprietary, and then you may have a system like BACnet with its own type, maybe it's a Jace, okay? But at the end of the day, what your building could probably stand to do if they want this scenario, which they do, they just may not know it, sounds like you know it, we can take out whatever those other proprietary front ends are, replace them with a Jace, and have everything talk to everything. So then you can...
Individual building needs to have a Jason to communicate back to the main source.
Correct.
Maybe within that building, you may have to have multiple.
Yep, may have to have multiple
You
Jaces.
could have N2, you could have a Delta on the bottom, you could have a Honeywell on the top, correct? All the same.
Well, also remember too that the Jace can accept all, like in this scenario, I should probably take those off. They're just up there. They're not connected to anything. They're just there for looks. You'll notice that all this is wired back into this one Jace, and it's all different. So the whole point is that all these different languages, communication protocols, all go back into that one Jace, and the Jace does the translation for them and spits it out.
So if you have different Jaces, they're all going to communicate together if you have 1 or 2 or 3 in a building?
Right. So the reason that you end up having more than one Jace almost always is because you've filled up that one Jace with as much as you can possibly do. So then you just add another Jace, and then eventually what we're going to get to is that these would eventually be wired in, and they'd go up here into this supervisor, which is basically like a master Jace.
No matter if it's different companies coming in and putting in their products.
Well, that's the thing, is that you've got to have this Jace in that building pulling in all these different communication protocols, and then however many Jaces you need are fine, but those Jaces, remember, they can talk to anything. Does that answer your question?
But different manufacturers' Jaces, if there are neither Jace, can talk to each other.
Question,
Sure.
and for clarification purposes, can you or can you not take a BACnet device and put it on a LAN network?
No, you can't. Well,
Right.
you can or you can't, depending on how you want to, because we can put them into that Jace, and they can talk to each other, but I couldn't take this LAN controller and stick it on this BACnet network. It wouldn't know what it was doing because it doesn't talk that language.
Okay, so what's your solution on that one?
So then we would run a LAN trunk. So we daisy chain all these LAN controllers in. Boom. We can just do one. We don't have to have multiple. We don't have to daisy chain if we don't want to. Obviously, in every case you're going to. So we have our LAN trunk and we have our BACnet trunk. We pull them into the Jace. Let's just go ahead and get ahead here for a little bit.
Because what you said, Niagara, you would have a dedicated case?
No, so
We're gonna get.
you'd go more into this part too, What the Jace does is basically take.
We're here now. I just had to get to that part. So essentially what's happening, all these different field devices talking all these different languages, we're pulling into that Jace via those wiring that we talked about in the system architecture. Then what happens is that Jace does a process called relativizing, and it creates Niagara points, which is the common language that everything can speak at that point. All right? So they've come up with one unified language that they can essentially bring in BACnet LAN into whatever it is, into the Jace, turn it into a Niagara point, and then everything on that Jace level that gets pulled in, all those controllers and all those points and set points and space temps and pressure variables and all that kind of stuff gets pulled in, and now it's turned into one of these 4 Niagara objects, which is that common language.
So if I got 100 different buildings, and say 100 different Jaces, no matter what brand it is, and one person in control, is it all going to communicate together?
It can.
Okay.
If you're, and that goes with licensing too, Carl. Yes, all the, you can get Jaces, any Niagara Jace, I should say that because there's an older R2 system that's going away. But Niagara Jaces can talk to each other over a common Niagara network. And it doesn't matter the brand.
You can't hold back on that one picture real quick,
Which one?
the one you just left.
The Niagara points.
The Niagara, yeah. What do you call it?
Sorry, that was only 27 clicks.
Are you going to be able to email out the PowerPoint?
Sure, I can do that.
Yeah, that'd be great. So it's numeric, Boolean,
Enumerated and string. So until you get into programming a Jace, it's not stuff that there's a 5-day long class that gets you AX certified, which gives you the fundamental level of understanding to be able to program a Jace. And then from
Understanding, the person needs to be there too, like the person in control.
to control it,
They have all
you do like an end user training or something like that, which sometimes your contractor will do for you. If you don't have, you can, yeah. So we can set you up where you come in just to learn how to use the graphics and that type of stuff, and do some various set point changes and that kind of stuff.
That's the problem they have. They're spending thousands and thousands and thousands of dollars, and nothing's communicating together to regulate temperatures in all these different buildings.
Gotcha.
Because there's too many different types not communicating together.
thank you.
No problem. All right, so your Jace is responsible for all of this stuff. Scheduling, it's going to write a schedule for all of these controllers to follow. Now we can have several different schedules. We're not set up where we just have to have our 1, 8 to 5, we're open and closed type scenario. We can have a schedule that says, here's our holiday schedule. So we're a school. Here's all of our teacher work days. Here's all of the early releases. Here's all the holidays that come about. And we can have schedules that override all those schedules so that your building is only operating when there's people in it. You can come in remotely and make schedule override. So obviously, school closure, there's snow. No one has to drive into the building and do all that stuff, like Snowmageddon. That was impossible, right? There's a superintendent or whoever it is that's in charge of maintaining those schools that logs in from the house and views all that stuff and never leaves. Some of them probably spent the night at the school, but that's another story, right? So alarming. So we talked about, to save you guys trips of running up however many flights of stairs or riding the elevator up to the 55th floor with your ladder, right? We can get an alarm. We can get that alarm sent to our smartphone, an email. It goes into an alarm portal where we have to acknowledge it to basically say, hey, I went and looked at it. This is what's going on, etc. All that's done at the Jace. You can do all of your data sharing. So like, if you need to know what the space temp is on this controller, if this guy needs to know what the space temp is for something that it needs to do, you can do that. You can share information from one controller to another. Smarter control.
But you're going through the Jace to get there.
Yep. All right, all this is telling us is basically that there's remote access, all right? So we're gonna connect this Jace to that building's internet, just like we would this here with a little bit more security. And then at that point there, you can access this from your laptop or any web browser, any smartphone, anything like that, okay? All right. You may or may not ever have to do this, but I thought I'd put it there anyway. When you buy a Jace, it's like buying a car. You choose your options afterwards, right? So when I go and I buy my Jace, I've got to determine what communication protocols that I want to talk to. So if I want to talk to LAN, I need that LANWorks option card, which is a physical card that plugs into one of the two COM ports on that Jace there, and then I can pull my LAN wire in, all right? If I want to talk to BACnet, I would need that dual port RS-485 card. Now what's the neatest thing about that card is we sell more of these than any of these other cards, probably times 5 or 10, because RS-485 is the network that BACnet, Into, Modbus, Train, all those speak that RS-485 language, and their BACnet stuff sits over top of it. So that's a lot of times why you have a dual port RS-485, because I can actually take that one card, plug it into one of my two slots on my Jace, and I can use one of those two ports on the card to pull in my BACnet and pull in my N2 all on that one card. If you really want to get tricky, in reality, you could pull in, I don't know, 5, 6, 7 different protocols at least on a Jace. Now you're probably never going to have to do that because there's not really probably going to be a building anywhere that has that many different communication protocols. But I could essentially put 2 RS-485 cards in there with 2 ports each, which gives me 4. So now I can do 4 protocols there. There's an onboard RS-485, I can put another one in there. And then getting really advanced, I can actually take any of those protocols, the majority of them, convert them into IP, which is Ethernet, like you plug into get your internet, put them into a switch and suck them in that way. So infinite possibilities. So you're never going to have to get a second Jace because you need to speak to more protocols than you can. You're almost always going to have a second Jace because you've put too much into that first Jace where it's going to slow down. You have to get another second Jace, right? Does that make sense? All right. Now, it doesn't stop right there. You basically, you know how when you have to get the driver as well. So that RS-485 card, like I said, talks to several different communication protocols. And when I install it, it doesn't do anything until I install the driver, which says, hey, this card is going to be used for BACnet. If I wanted to use this card for Metasys, the Johnson Controls N2, then I'd put that driver in. The driver is, you know how when you plug your mouse into the side of your computer for the first time and Windows makes that dun-dun-dun sound, and then you see the little thing that says updating driver or installing driver software. Essentially, you've got hardware and software. All right? At our first break, do y'all have any questions?
I had a question.
Sure.
Probably a stupid question.
No stupid questions.
See how the Jace will actually hook up to Metasys. So like, let's say you got a building that's got like a bunch of Metasys DX9100s, the Johnson Controls setup. Let's say that you're trying to do away with Johnson Controls front end. Could you take that Jace, since it'll communicate with all that, and then take another front end, communicate with that, and then do away with Johnson Controls
Yeah.
and their components?
So, excellent question.
Be a cheaper way than having to replace all the controls.
So what we're going to do is we're going to have, and this is going to be a really crude drawing, okay? So we're going to have, this is our N2 or our Metasys, right? And we've got our controllers on here in our building, and then we've got their head in somewhere. It's probably called an NAE. All right, so what we would do is we would take and we would do away with that NAE, and we would install our Jace. And our Jace would pick up all of our N2 in there, so we're good to go. Now, what most people do is the goal is to ultimately get away from this altogether, right? But now I can come in and say, I'm going to give you a price to replace your front end and do that programming, or I'm going to give you a price to do that plus take all this away and replace it all at one shot. Most people opt to not do that because they don't have to. So what people do is they run a second trunk. Let's just say for this one, it's going to be BACnet. And then what happens is that we're just going to run this trunk, and we're going to go in there and we're going to say, okay, we found out that this controller was bad, it never talked, and this controller was bad, it never talked. Or we're just going to replace it. Now what we're going to do is we're going to put that controller there and that controller there on the BACnet network. And remember, once it gets back to the Jace, it doesn't know where it is, right? So to you, the guy sitting there in front with in front of your graphics, you don't know really at the end of the day whether it's N2 or BACnet. It's all pulling into here. Remember that little screen where it did the little relativizing thing? And at that point, they become Niagara points.
And you take that to another front end?
Well, if you only have one Jace, you don't need to.
Yeah, give that same front end. What you're doing though is you're giving the possibility to eliminate, to phase out that Metasys over time.
Right.
And have to spend all that money up front,
You got it.
which, that's
That's a
smart.
very useful thing.
Yeah, it is. Because Johnson Controls has got theirs on lockdown, so
Right.
if you call them, they don't want to give you the information. I could take that and do away with them.
Right.
Phase them out.
You got it.
They hate to hear that.
Great question.
Well, maybe a little bit more friendly.
Anything else? Any other questions?
Isn't Johnson Controls phasing out the Metasys N2?
Yeah, so they're using BACnet now. And we're going to talk about open versus closed here in this next little bit. And I'm going to talk to you about why their BACnet's a little different than our BACnet and how all that ties in and works together.
It's amazing how they, ASHRAE originally wanted the BACnet so that everybody could talk to each other. And the only people who really embraced that was the second tier type EMS guys.
Yep.
Delta, ALC, or, different ones. But it's so nice to be able to walk into a system that's got a good BACnet setup.
Yep.
You can remotely do a lot of things.
Yep.
I mean, the big box guys can monitor a whole lot of places throughout the country.
Yeah.
And it's very strong, whereas the big four, they fought it for the longest time.
Yep. Yep. It's good stuff. All right. It's about 9:15. Let's get back here at 9:30.